here's a problem where we're solving for a lot of different angular and linear quantities using the derivative of the position function. So we are given the radius of this amusement park ride, and we are also given the function for theta versus time. So it's written pretty small here, but I'll write it larger. CT cubed, and we're given what the constant is. And they want us to find all these quantities at this certain time. So what's happening here is that a person's going to stand against the wall. So they're going to stand right here. This is like a top view. And after they get in the ride, obviously it needs to speed up. It's going to spin in a circle. But we're talking about the speeding up phase of this. And so I drew the vectors in here, which could represent either, I guess let's call these maybe centripetal acceleration is the red vector. And then there's also some tangential acceleration because the ring that this guy or person is riding in is speeding up. So then the overall acceleration here points at an angle. That's what they're asking for here. Let's write all the abbreviations in. This is omega. This is V, like we're used to. And then we have alpha here. We have AT, tangential acceleration. Your book calls it radial acceleration, but we tend to call that centripetal acceleration. And then overall acceleration would be the vector sum of AT and AC. Okay. Well, to find angular speed, that's the first derivative of angular position. So that's not bad. We just use the power rule here. So if I'm going to do that, I would show that omega as a function of time is d theta dt. So then I would write that as 3ct squared, and I'm evaluating that at 2.2 seconds. So omega at 2.2. So then I'm doing 3 times 0.0639 times 2.2 cubed, or sorry, squared. So when you do that on your calculator, then we get 0.928. And notice if I'm doing an analysis here that it does come out to be radians per second when I include the units from C. So that's a good sign because I wanted that unit for omega. Now to get linear speed, this is on the pink sheet. Toward the bottom, it will tell you linear speed is just radius times omega. So that's easy. I'm going to take my 33.1 meters because the rider is at the farthest edge of the circle, and just multiply by my omega value. Now radians, remember, is really just like it's kind of a fakey unit. It's like a ratio, so I wouldn't do meters times radians over seconds. I can just sort of get rid of the radians when I do the units, so that now I'm back to having meters per second. Okay. Oops, 30.7 meters per second. Then, that's pretty fast. Then we're gonna let's do angular acceleration alpha. So, switch gears here. Now to find alpha at this time, I would need to take the derivative of the angular velocity function. So, taking the derivative of 3ct squared, and I'm going to get 6ct. So then evaluate that at 2.2 seconds. Sorry, I have missed the units here. Okay, there we go. And we will get 0.843. This becomes radians per second squared, which I expected. Okay. Then, next I could do, what's next on my list? Okay, tangential acceleration. So then AT, I can get by multiplying my alpha value by r. So when I'm getting the linear quantity just by multiplying the angular quantity by the radius. This one isn't on the pink sheet, I can't find it, but that's something you can remember, is that all I have to do to get the tangential quantity is just do the angular quantity times radius. Okay, so then I got 27.9. Okay. Ooh, I should have written this in blue. So, but let me go back up here. So this one is actually the 27.9. That's what I just found. Okay. Then let's find the centripetal acceleration. So for that one, remember we always used to use, this is for the part of the acceleration that points toward the center of the circle. There are two ways now. We could use either this equation or this one. So pick or choose. If I'm going to use, for instance, the first one, because we're more used to that one, then I would say this is referring to our speed. So we've got, well, but remember, I shouldn't use that one because it's not constant. So I wouldn't want to plug in 30.7 meters per second. Well, oh, well, neither is omega. So all of this is changing at every moment, but since I'm evaluating at 2.2 seconds, that's fine. So either way, I've got, these are changing at every single second, so I can use either one. Okay, 30.7 meters per second. Squared. Okay. So then, okay, 28.5. Then that would be this value. Looks like my picture is not just Gil. Okay. Last thing is the overall acceleration, the hypotenuse basically, of the triangle that is made by AT and AC. So now I'm going to use Pythagorean theorem to find overall acceleration. So once I get that 39.9, that's the magnitude. Okay, and then I could also get this angle if I would like to know what this angle is, right? Imagining, scoot this over. Oops, maybe that helps me picture it better. Nope, sorry. So this is AT, and so then if I want to know this angle, that would be opposite over adjacent, tangent, inverse tangent of AT over AC. So theta equals, or maybe I should, theta's overused here, but this angle is inverse tangent of a T C, and when I do that, I should get almost 45 because they are almost equal. 44.4. Okay. So notice they don't use radians now. At least the book doesn't. So then this would be 44.4 degrees right there. Okay.